In a recent paper, Otten and Gray proposed a multidimensional generalization of polynomial zero-noise extrapolation (ZNE) for systems with non-identically distributed noise models. This method aims to recover the ideal expectation value of an observable of interest using noisy intermediate-scale quantum (NISQ) machines. However, the measurement overhead required for this protocol increases exponentially as a function of the number of noise sources and the multinomial approximation order, making it impractical from the perspective of quantum computing. The concept of one tunable global noise parameter is often misinterpreted in the literature. It does not refer to a single noise rate that defines every interaction in the system, but rather means that every rate of each noise source can be increased by the same proportion. This is clarified by the definition of a tunable global noise source, which refers to the fact that the rates of each of the noise sources affecting the qubits of the processor can be tuned by the same factor, g. The noisy expectation value can be expressed as a multinomial expansion, similar to the one obtained in 1. However, if we amplify the noise rates of the system in a uniform manner, i.e., by multiplying each rate by a factor g, the multinomial expression can be written as a single variable polynomial over the free variable g. This allows for the application of standard ZNE methods, too, with the same amount of measurement overhead as for the single noise rate case. The authors in 1 discuss that their proposed method presents an unbearable experiment repetition overhead, making it impractical. However, the traditional extrapolation techniques can be applied to the setting discussed by Otten and Gray, reducing the overhead of the protocol. Multiqubit systems with arbitrary noise sources and rates can be efficiently used to extrapolate ideal expectation values of observables. The function that is being fitted is a function of the amplifications g and not of the noise rate. The base noise rate, lambda 1, will determine the bias that the estimate will have, lambda 1, 2. Following this logic, a similar approach can be taken for the setting in equation 1. The noisy expectation value can be expressed as a multinomial expansion, and if we amplify the noise rates of the system in a uniform manner, the multinomial expression can be written as a single variable polynomial over the free variable g. This allows for the application of standard ZNE methods, too, with the same amount of measurement overhead as for the single noise rate case. In conclusion, the requirement of one tunable global noise parameter is not a limitation for the application of ZNE methods in multi-qubit systems with non-identically distributed noise models. Instead, the amplification of each noise source by the same factor g allows for the use of standard ZNE methods, reducing the measurement overhead of the protocol and making it more practical for quantum computing. In the context of quantum computing, this research paper discusses the concept of zero-noise extrapolation, ZNE, and its application in mitigating errors in quantum processors. The authors address the misconception that ZNE techniques are not applicable to multi-qubit systems with arbitrary noise sources and rates. They clarify the meaning of a tunable global noise source, which is essential for reducing the measurement overhead in ZNE. The paper also explains how amplification protocols, such as pulse stretching and probabilistic error amplification, can be applied to achieve this requirement. The authors show that the method proposed by Otten and Gray in 1 has an impractical measurement overhead for quantum computing applications due to the large number of samples required. In contrast, standard ZNE techniques can be applied to reduce the overhead to practical values, as demonstrated in 13. The paper concludes by highlighting the need for future studies to consider the reduction of the measurement overhead of the method proposed by Otten and Gray, possibly through sparsifying the feature matrix. The research paper delves into the realm of quantum error mitigation techniques, focusing on the optimization of Richardson extrapolation for enhancing computational reach in noisy quantum processors. It references various studies that have contributed to this field, including those by Kandala et al. 6, Krebsbach et al. 7, and Jurgica-Tehran et al. 8. These works emphasize the importance of error mitigation strategies to extend the capabilities of quantum computing before achieving fault tolerance. The authors also discuss the role of coherent errors and their transformation into Pauli noise through twirling. 12. This transformation simplifies the analysis and allows for the application of existing error mitigation techniques. Furthermore, they cite studies on the performance of surface codes in realistic quantum hardware. 4, 5, and the unification and benchmarking of state-of-the-art quantum error mitigation techniques. 10, 11. In addition to these references, the paper explores time-varying quantum channel models for superconducting qubits. 14, 15. These models are crucial for understanding the dynamics of quantum channels in NISQ superconducting quantum processors. By considering multi-qubit time-varying quantum channels, the authors aim to improve the efficiency and accuracy of quantum computations. Moreover, the study highlights the significance of quantum error mitigation in enhancing the performance of quantum algorithms. It emphasizes the utility of quantum computing even before achieving fault tolerance, as demonstrated by Kim et al. 13. This underscores the importance of continued research in this area to maximize the potential of quantum computing. Overall, the paper provides a comprehensive overview of quantum error mitigation techniques, emphasizing their role in extending the computational reach of noisy quantum processors. It highlights the importance of optimizing Richardson extrapolation and other error mitigation strategies to enhance the performance of quantum algorithms.